Hello everyone, this is Mr. Couple. Welcome to our second week of online instruction. Today we're going to be learning about charge polarization, electric fields, and electric potential. I'm joined in voice chat today by several students. If you guys could please say hi, that'd be great.
Hi.
Hello.
So Mauricio and Justin, is anyone else joining us today?
Hi.
Is that Jamie?
Yes.
Making me recognize your voices. Cool. I think also Christina is here for a little bit, and so is Mayar. Okay, let's get started. So first, I'm going to show you guys this video of my son. A couple years back, we recorded this funny video. So I rubbed a balloon against his hair and then pressed it on the ceiling, and it stuck to the ceiling. So I'm going to show you guys this video. Oh, I don't even hear anything. Oh, the audio's turned off. Okay, let me try this again. Muted.
I want to try
Just-
Okay, here, I'm going to
charge it up. Okay, I want to do it this time.
Okay, now you charge it up.
I want to do it this time.
Okay, here we go.
I want to try
Just
this.
wait, we're gonna make it stick. Oh, it's stuck to the ceiling. Oh, don't fall. Danger zone. Bodhi, why is it? Tell. Dude.
Okay, so the mysterious behavior of the balloon is that it's sticking to the ceiling. So this is really weird because what we learned was that opposite charges attract. But in this situation, only the balloon is charged. So when the balloon is rubbed against the hair, the balloon picks up, let's say, a negative charge. And then if we bring the negatively charged balloon up to the ceiling, it sticks to it. How is that happening? Why would a charged object be attracting an object that's not charged? So why does the charged balloon stick to the neutral ceiling? Do you guys have any ideas?
The ceiling still has. Never mind.
Never mind. Okay. So what is the ceiling made of? So the ceiling is made of atoms. But atoms have a neutral charge. So you have the same number of electrons and the same number of protons. So the atoms are neutrally charged. So there is no net charge in the ceiling. But in the balloon, there is a net charge because electrons have been transferred off his hair onto the balloon. So the balloon has picked up this extra negative charge. So this is weird. Like, why would a charged object be attracted to a neutral object? And so this is a weird counterintuitive thing, but this is actually true. Neutrally charged objects are attracted to charged objects. Neutrally charged objects are attracted. Neutral objects are attracted to charged objects. So there's this simulation that I'm going to show you guys. This is a PhET simulation, and I'll post this in the assignment on Google Classroom so you guys could play around with it. But the basic idea is this. Let me move my camera. Okay, so the idea is I'm going to take my balloon. Right now it's neutrally charged. It has the same number of positive and negative charges. I'm going to rub it up against the sweater. It's going to pick up some negative charge. And you can see that it's now strongly attracted to the sweater because opposite charges attract. Then I bring it to the wall, and now look closely, but the negative charges in the wall are pushed away from the balloon, leaving the surface of the wall, or the ceiling, to be positively charged. And so now when I let go, the balloon sticks to the wall. So we can see that the balloon is actually attracted to the wall because the negative charges have been repelled by the negatively charged balloon. So what has happened here is that the balloon has induced a charge in the ceiling. So the formerly neutrally charged ceiling becomes positively charged on its surface, and then the balloon is able to attract to it. All right, so back to here. So the basic idea here it is. The electrons in the atoms of the wall are pushed away by the negatively charged balloon. You can see the atoms are pushed away. So the electrons are pushed away in the atoms, leaving the surface with this overall positive charge. And so now the negatively charged balloon will attract to the positively charged surface. Neutral objects are attracted to charged objects. So we want to try to understand this a little bit better. So to help you guys understand this, let's look at an atom. So here's my questions, and I want you guys to just shout out the answers. So what is the charge of an atom? So here's a picture of an atom. What is the charge of an atom?
Neutral.
Yeah, it's neutral. So give me that as a number.
0.
So there's zero charge. So we can see that there's +5 in the center. What the heck did I just write 15 for? So we have +5 in the center and then minus 5 from the electrons, giving us a total of 0 charge. Where are the centers of the positive and negative charge? So the positive charge is here. So where's the center of that? Well, the center of that charge is right there at the nucleus. Where's the center of the negative charge? So the negative charge is around here. Where's the center of the negative charge? Also at the center. So what happens is the centers of both charges is in the center, in the nucleus, in the center. But now what we're going to do is we're going to bring a negatively charged object, and that would be the balloon, an external negative charge, and we're going to bring it towards the atom. And then look what happens. As that negative charge is brought towards the atom, all those electrons that used to be over here, what happens to them?
They're repelled.
They're repelled. They end up being pushed and squished over to the other side of the atom. So what ends up happening is you get the center of charges gets shifted. So what happens to the center of charge? Well, the center of the positive charge is still here in the nucleus. But look what happens to the center of the negative charge. The negative charge center is now out here. So there's your center of negative charge, but your center of positive charge is still over here. So now this object no longer acts like a neutral object. It actually acts like a charged object, where you have a positive charge on one side and a negative charge on the other side. So it's no longer acting like a single neutrally charged object. It's acting like two separate charged objects. This is called electrically polarized. What's up?
Does this charging of neutral objects, is it happening through induction or contact?
This is induction. So they're not actually touching. It's the electric fields that are exerting these influences without touching. So you would say this is induction, that a charge is induced in the atom. We call it electrically polarized. So this is what happens. This is how you explain static cling. So I showed you guys this picture before we went on spring break, that the cat had all these little pieces of styrofoam stuck to it. And so the way to think about that is, here's each piece of styrofoam. And if the cat has picked up some negative charge, maybe the cat was rubbing against the carpet, or pushing up against something like a clothing or something like that. And so the cat picked up a bunch of negative charge. Now the cat has this negative charge. And so when the cat is then brought near the styrofoam, it polarizes. That's the word for this up here. It polarizes the atoms, leaving one side of the object, the styrofoam, to be positively charged, and then the other side of the styrofoam to be negatively charged. And so that ends up sticking to the cat. This positive side ends up sticking to the cat. So it's not that the styrofoam is charged, it's that the charge has been separated so that one side of the styrofoam is now positively charged, and it will actually be attracted to the fur on the cat. What questions do you guys have for me about this concept of charge polarization? So if you've never heard that word polarized before, so you think about the poles of the Earth. So the Earth has a North Pole, and oh my gosh, what is it? A W pole? The Earth has a North Pole and it has a South Pole. So we say things are polarized when they're pushed to two extremes. So instead of things being neutral in the center, they've been pushed out to the extremes, and it's been spread out and it's become polarized. You'll often hear this used in politics, to describe the state of the nation. We're really polarized. There's a lot of arguments against two sides of the political spectrum. But it's a scientific word. It just means when two things are separated to extreme opposite values. And so that's what's happening, is our atom is going from being unpolarized to being polarized by this external charge that's pushing the electrons away. You'll also notice that there is a slight effect where the nucleus is attracted to the left, and then the electrons are pushed off to the right. So that's charge polarization. I just thought I'd mention it to you guys because it kind of seemed to fit in well based on what we were talking about earlier. Okay, next thing we're going to talk about are electric fields. So electric fields are very similar to gravitational fields. So rather than like teaching you a new concept, I'm just going to try to introduce this to you guys by comparing it to gravity. So we've seen this picture before. The idea of a planet going around the sun is very similar to the idea of an electron going around an atom. They're very similar systems to each other, except one is the gravitational force and the other is the electric force. All right, so let's write out some equations first. So you may not remember this equation. It's okay if you don't remember it. The gravitational field strength equation, it's G, little g, that's the gravitational field strength. On Earth, it's, remember what it is? Someone should say it. What's the gravitational field strength on Earth? At the surface of Earth.
-9.8.
Got it, it's 9.8. Or -10, whatever you want to call it, that's fine. So G, actually the way you get G, the general equation, is it's the force divided by the mass. And so you could see that if you solve that for force, you end up getting mg. If we multiply both sides by m, then you get mg. That's just the weight equation. So if we solve the weight equation for the gravitational field, you get G equals F over m. For electric field, it's almost the same. The difference, though, is that we don't use G for electric field. We use E. Even though E stands for energy, we use the same letter. I know it's a little bit confusing. Sorry for that. That's just how physics is. So the electric field strength equation is the field strength E is equal to, it's the similar thing. It's force, but if you remember, electricity doesn't use mass. What does electricity use?
Charge.
It uses charge. So that's going to be Q. So E equals F over Q. If you solve that for F, you get F equals Q E. And so that's like your mg equation for electricity. So we say weight is mg. You can say that electric force is QE. Okay, here are some questions. How are gravitational fields created?
When one mass is placed near another.
So the field doesn't need two masses, it only needs one mass. So the planet is creating a gravitational field. I'll draw it in there. So this is the gravitational field. And it pulls anything else towards it. Anything else that has mass gets pulled towards it. What creates the field? All you need to create a gravitational field is you just need this property. Mass. And how are electric fields created? The analogous quantity to mass for electricity is?
Charge.
Charge. You got it. So what do gravitational fields do?
They attract objects.
They attract objects with
Mass.
mass.
Gravitational fields.
Gravitational fields attract objects with mass. What do electric fields do? Attract.
And repel.
Yeah, they do. Yep, objects with
Charge.
Objects with charge. There you go. So so you can see how they're very similar with respect to each other. So the Earth, or the planet, I should say, is creating a gravitational field which attracts the moon or the satellite towards it. Similarly, the proton creates an electric field which attracts the electron towards it. And that's what's keeping the electron in orbit around the atom, is the nucleus attracts the electron. So you have a very similar setup. It's almost exactly the same. So just think about electricity as you would gravity. They're very similar to each other. The major difference, right, there's two differences. Difference number one, instead of mass, for electricity, we use charge. And instead of always attracting, electricity can also repel. Otherwise, they're very similar forces to each other. It's the similar equation, similar force description. Everything's very similar. The other difference that's not here is that electricity is way stronger than gravity. All right, so now let's introduce this idea of a field. So I'm going to pull up this other simulation. You guys know how much I love these PhET simulations for teaching online. I think I've been giving you guys like a whole bunch of these. I'm going to turn off the arrows and just show you this. Okay, so if I've got this positive charge just hanging out here, and let's bring in a sensor. So this sensor is measuring the force that this charge would exert. It's showing us the magnitude by the length of the arrow, and it's showing us the direction by the direction that the arrow is pointing. And so you'll notice that if I move this detector around different places around this positive charge, you can see that I'm getting different amounts of force. As I get closer, the force gets stronger, and as I get further, the force gets weaker. What we want to do is we want to capture some description of this influence that this charge has on the space around it. We want to try to capture that information. And the way we do that is with the concept of an electric field. So I'm going to go back to here. So the idea that we say is that charged objects in the space around them create electric fields. And so if another charge enters the field, it's going to feel a force from the field. And so here are the key understandings that you need to know about electric fields. The first is that charged objects create electric fields. So in order to create an electric field, you have to have charge. So that's the first key understanding. What is it that creates electric fields? Anything that has charge. Whether it's a positive charge or a negative charge, it's going to create an electric field around it. And so here's the electric field around a positive charge. Here's the electric field around a negative charge. The second key understanding. When a charged object is placed in an electric field, it feels a force from the electric field. So these lines are representing the electric field. This electric field is pointing to the right. I don't know. Wait, that's probably this way, pointing to the right. So if we put a positive charge in the field, it's going to feel a force, and it will be pushed to the right. So there'll be a force on that positive charge. I'm going to try that again because I'm having trouble with the angle that I'm at here. There we go, force. So the positive charge is going to be pushed by the field. It's going to be pushed to the right. So those are the two main ideas. Electric fields are created by charge, and if another charge is placed in the field, it'll feel a force from the field. Okay, next.
I have a question.
Yeah, ask your question.
Sorry, but
Don't apologize.
Charge is scalar?
Charge is a scalar. Yeah, charge is a scalar. So if you look at the equation, it's F equals EQ. Wait, no, I did it backwards. QE. Doesn't matter which order. But you'll notice that charge is just like mass. It's a scalar. So charge doesn't have direction. So where does the direction of the force come from? It comes from the direction of the electric field. So whichever direction the electric field is going to point, that's going to be the direction the force points. Now, where it does get a little bit tricky is that a positive charge will go the opposite direction as a negative charge. And that's what I'm about to show you down below. So the charge does matter, because if you have a negative charge in there, then the force would actually point opposite to the electric field. But if you have a positive charge in there, then they'll point the same direction. Is that helpful?
Yeah. So is electricity a vector?
When you say electricity, you got to be specific. Are you talking about the electric force?
Force or field?
The electric force is a vector, and the electric field is a vector.
Okay.
Yep. Okay, the next key understanding is the direction of the electric field is the direction a positive charge would be pushed. So if you look at this picture here we have some unknown charge, but we know the field around it is pointing away from it. So what must the charge of this object be? It has to have a charge because it's creating this electric field around it. The question is, what is the charge of this object?
Positive.
It has to be positive. So how did you figure that out, Mauricio?
Since the arrows are pointing away from the...
Yep, the arrows are pointing away from it. So you imagine if there were a positive object here, what would happen is it would be repelled. It would get pushed away. So that means that because of this rule, the direction of the electric field is the direction a positive charge will be pushed. We could see that a positive charge would be pushed away from a positive charge. And so that's how we know that those arrows have to be pointing. If the arrows are pointing out, then it has to be a positive charge. What if it was a negative charge in the center? Then how would that change things?
The direction of the positive charge would be towards it.
Yep, so the field would just turn around. And I don't need to draw that because I have the picture of that up here. So you can see with the negative charge, the field was pointing towards it. With a positive charge, the field is pointing away from it. So the direction of the electric field is the direction a positive charge is going to be pushed. And that's by convention. That's how we decide to do it. So if we had a negative charge in an electric field, a positive charge would be pushed to the right. which means that a negative charge would be pushed
To the left.
No.
to the left. So negative charges always go against the field or opposite to the field, and then positive charges go with the field. And then the last thing you guys need to know about electric fields is that the density, or how close the lines are, that tells you how strong the field is. So in which situation, A or B, do we have a stronger electric field? So is the electric field at A greater than, less than, or equal to the electric field at B?
Greater than?
And how do we know it's greater than?
Because the lines are closer together.
So the density of the field lines tells you the strength. When the lines are closer, the field is stronger. When the lines are further apart or less dense, the field is weaker. You can see that here. As we get closer to the atom, so if I draw a circle right there, that radius away from the atom, or I don't know why I'm calling it an atom, but from that center positive charge, when we're at this distance, the circular radius distance here, the lines are really close together. Like, look at how close together these lines are. But then as we go further out, the lines get further apart. The further apart the lines are, or the less dense the lines are, the weaker the force gets. So if you just imagine, if I'm just staring at this thing and I'm starting to like move away from it, you can see that the lines are getting further and further apart from each other, which is representing that the field is getting weaker and weaker. And so the force would get weaker and weaker because of this equation. Where did I put it? Up here. So as the field gets weaker, the force gets weaker. It's a direct relationship. There are three important fields that you should know about as we move forward into other areas of electricity. The first field is this one, which is the field around two equally charged objects. So let's call this guy a positive and this guy a positive. So now what will happen is the fields from one and the field from the other, they will actually superposition or superimpose on top of each other, and they'll actually end up creating a blank space in the center where there is no field. So the field here at the center is 0. And that's to signify that if you were to place a positive charge there, it would be repelled from the one on the right, and it would also be repelled from the one on the left, and then you would have equilibrium. There'd be no net force on that charge. And so that's why there's a hole in the center of that field. You can also see that they're pushing away from each other, and so this is to signify that they're repelling each other. So you can see that they're both positive charged. Man, I should not have drawn all these arrows on here. This is taking me 1,000 years to draw them all. But I'm pointing these arrows away from it because a positive charge would be repelled from these objects. So this field pattern, sort of this like diamond shape, you can kind of see this diamondy shape here. This is the field pattern for like objects. When they have like charge, they're going to create sort of this like diamondy shape. So what do you guys think it'll look like if they're oppositely charged? So it won't be a diamond shape. What do you think it'll look like if the particles have an opposite charge?
They'll just be touching.
They'll be touching. Yep. They're going to have to be like pulling together. So the field looks like this. So our positive charge here stays the same, but now this is a negative charge. And so now instead of the lines repelling and pushing against each other, they're actually pulled into the other one. So the electric field starts here and comes out from the positive charge, and then it actually ends up going in to the negative charge, forming this complete line from one to the other.
Kind of looks like a spider.
Yeah, you do get some large... your brain is trying to see patterns and look for things in there. I've heard spider, I've heard alien, I've heard like weird cartoon characters, all sorts of stuff. The last one is this. This device has a special name. It's called a capacitor. Capacitor. And a capacitor creates a uniform electric field. And the uniform electric field is in the center of the capacitor, so you can see that those lines are parallel and evenly spaced. That no matter where you go in between these, at any of these points, you have an equal electric field. So capacitor is basically two charged plates. It's like one plate has a positive charge on it, and then the other plate has an equal negative charge on it, an equal amount of negative charge. And it creates this really interesting pattern where the fields are exactly equal inside of it, creating this uniform electric field. And this is very useful for storing energy. So you can charge up a capacitor and then you can discharge it and create like a flash or like a sudden burst of energy can come out of this thing. So those are three important electric fields that you should know about as we move forward in the electricity unit. So ask me questions about electric fields, guys.
Can you show us like a video or a demonstration of a capacitor?
I could, but I don't have time for it. But how about I link to you guys a video of a capacitor? Would that be cool?
Thank you.
I'll link a video when I post the assignment. Okay, there's one last concept I wanted to talk about. I know I'm kind of running out of time. Looks like I got like 5 minutes. But the last concept is electric potential energy. So going back to the same idea of like this analogy between electricity and gravity, we can also think about energy. So we haven't talked about energy yet. We've mainly been talking about force. But if we think about energy, if you lift a mass off the ground, right? If I have this crank and I lift up this mass off the ground, we say that it has potential energy, but that's mgh, right? So since it's lifted off the ground, it has this energy stored within the gravitational system. When we let it go, when we cut the rope, the mass will fall down and the kinetic energy gets transformed from the potential energy, or the potential energy gets turned into kinetic energy. You can create a very similar situation with electricity, with charge. You just think, well, instead of having a mass, I have a charge. And instead of having a planet, I have another charge. And so as we lift this positive charge up from the planet, as we lift it up, you end up getting potential energy stored in this configuration, in this system. So that when I cut the rope, the positive charge will fall down just like the negative charge. And when it falls, it's picking up energy, like it's gaining energy. So when two masses, so I'm reading down here, when two masses are separated, the system gains gravitational potential energy. Likewise, when opposite charges are separated, you gain electric potential energy. So opposite charges are like gravity, but we also need to think about like charges, because gravity never repels, gravity always attracts. So we also have to think about, well, what if the charges are the same? And so here's that situation. So you can imagine if you have two like charges and I try to bring them together, like squeezing them together, that's kind of like squishing a spring. So if you push in the end of a spring and you push it in and you release it, it'll bounce back, and that potential energy stored in the spring will get released back out as kinetic energy. And it's a very similar effect to like charges. If I were to suddenly let go of this positive charge, it would go flying away, just like the spring would uncoil. So we say that when you compress a spring, the system's gaining elastic potential energy. But when you compress two positively charged particles, when two like charges are brought together, you're gaining electric potential energy. So electric potential energy is just more complicated than gravitational, because you can get electric potential energy from when two things are pulled apart, but you can also get electric potential energy when two things are brought together. That's the difference between them. I think I prepared way too much information for you guys. All right, so this device is the Van de Graaf generator. You'll remember like there's that picture of me like touching it and my hair like stood up on end. I also showed you a picture of a student who was touching it. So I have a few questions about this. We'll see if you guys understand it. If we don't, I'll just shut this video down and we'll start another video. So let's see. So at which location does the small positive charge, so I'm talking about this guy here. So at which location does the small positive charge have a greater potential energy, electric potential energy? So we have this positively charged sphere here. It's got a lot of positive charge built up on it. To charge up, if I were to touch it, that positive charge would transfer into me and my hair would stick up. So I'm asking which one of these guys has more potential energy? Which one is lifted further away? These are like charges. So like you have more potential energy when you're closer to it. So which one of these is closer to the sphere in the center?
They're at equal distances.
Yeah, they're equal distances. So they have equal PE because they have equal R's. They have equal radius. We call those dotted lines, those are called equipotentials or equal potentials. It's where the potential energy is equal all along that line. Okay, next question. The charge is now brought closer to the sphere. So what if I take that charge and I move it inward? So now I'm bringing it in closer. Is this an increase or decrease in the electric potential energy?
Decrease.
Yep, then the potential energy is going to increase. So it's being pushed more now. So at this distance, it was barely being pushed at all, but now it's like really being pushed. And so there'd be a greater push on it, so it could gain a greater amount of energy when it like boom, gets flung off of that thing, when it gets repelled from it. And my last question is, what if I bring this big honkin' charge, like this huge charge with way more positives, and this one, and I bring them to the same radius? So my question is, which one has more potential energy? The big honkin' charge or the smaller charge?
Smaller chart.
Smaller charge. So think about if I had like gravity. If I had a little mass at the same height, bloop, versus a gigantic mass at the same height, which one would have more potential energy?
Both of them.
Both of them. So potential energy is mgh. So they're at the same height in the same gravitational field. So which one has more potential energy is the one that has
More mass.
more mass. So which one of these two has more potential energy?
The larger.
The large, the greater mass. So likewise over here, this guy would have a small amount of potential energy, but this one would have a huge amount of potential energy. Because it has a greater charge, it's going to be pushed with a greater force, and that greater force is going to give it a greater acceleration, and so a greater amount of kinetic energy will come out of this arrangement. So it doesn't just depend upon how far you are, it also depends upon how much charge you have. It's just like gravity, it works very similar to that. So the one that has a greater potential energy is the one that has greater charge. So I'll write that down. So if Q goes up, then potential energy goes up. It can be useful to define a quantity that depends only on the charge of the sphere. So here's the thing, like there's lots of different charges that we can stick in this field, and in the field being these pink lines here. So there's lots of different objects that I can stick in this field. And you know what? I want a quantity that tells me how strong, how much energy this charge object, I want to find out how much energy is this capable of giving to another object. And I don't want that to depend upon what object is put in the field. I want it to depend on just that object. And so it turns out that you can do this fancy math thing where you can take the actual electric potential energy and you divide it by the charge, and it gives you this quantity called the voltage or the electric potential. We're going to talk all about voltage in the future. It's not key that you understand it now, but just realize that voltage is independent of the charge. So we've taken what depended on charge, so the potential energy depended on the amount of charge, and we've divided out that dependency. So the voltage doesn't depend upon the charge. The unit of electric potential it's called the volt, and so that's why a lot of people just call it voltage, but it's really supposed to be called electric potential. So what we say is that a volt, and you guys have all heard this before because you've heard volts like with batteries and things like that. A volt is a joule, a unit of energy, per a coulomb, which is a unit of charge. And I'm just going to end with showing you guys this cool little chart. Actually, I should probably pause and have you guys ask me questions, but I assume you guys probably don't understand what's going on, so you probably don't have any questions. If you have any questions.
You're not wrong.
Yeah, this stuff is really weird, and this is just an introduction to it. We'll be getting more into depth on it as we go into circuits and electricity and stuff like that as we continue. But all I want you guys to take away from this is that voltage doesn't depend on charge. The charge is canceled out of it. So we would say that this sphere, I think it's down here. So this sphere, the Van der Graaf generator, has 100,000 volts. That's a high voltage. For comparison, a lightning strike has 300,000 volts. So here's me touching this sphere. That's 100,000 volts of electric potential. That's equivalent to a lightning strike as far as the potential goes. So why aren't I getting killed? Likewise, a battery is only 1.5 volts. Like batteries there's nothing to be worried about, right? Batteries are simple. They're fine. But the thing is, if you look at this equation up here, it's not just the potential, it's not just the volts that matter, it's the charge and the amount of energy. So if we actually look at, well, how much charge is on this sphere? So how much charge is down here? It ends up being, it's about 0.000001 coulomb. It's a million, what is that? Yeah, like about a millionth of a coulomb, or I think that's around a microcoulomb. So it's like a millionth of a coulomb. How many coulombs are in a lightning strike? It's about 15 coulombs. And how many coulombs are in a AA battery? If you were to fully discharge the battery, like plug it in and let it drain completely, how much charge would be flowing out of the battery? It's 5,000 coulombs. And so if you go to calculate the electric potential energy, so up here, the potential energy is the electric potential, the voltage times the charge. So the potential energy is the voltage times the charge. So if you multiply these two things together, that tells you how much energy there is. So the reason I'm not scared of touching the Van de Graaff generator, even though it's 100,000 volts, is because if you multiply these two numbers together, you end up getting a very small amount of energy. So let me pull up my calculator. So if I take 100,000, I can't see. Here we go. If I take 100,000 volts times 0.000001 coulombs, I end up getting I end up getting 0.1. It was here. I end up getting 0.1 joules. So this thing is only transferring 0.1 joules, which is nothing. Like, that's imperceptible. Like, you will barely even notice it. If you multiply 300,000 times 15, so for a lightning strike, 300,000 times 15, you get 4.5 million joules. So you get 4.5 megajoules. And that's enough to kill you. That's a ridiculous amount of energy that will kill you. And if you multiply this for a battery, what's that? Like half of 5 is 20. That's like 7,500 joules. I'm going to be very embarrassed if I didn't do the math right. So I was thinking 1 would be 5,000, and then half of 5,000 is 2,500, so 7,500 joules. Okay, that's it, guys. If you have questions, you should ask now. Otherwise, I'm done. Okay, hope you guys have a great day. I'll see you later.